I want to tell you about the day I realized that everything I thought I understood about reality was just a comfortable lie I'd been telling myself. It happened when I was watching a single electron, just one, do something that should have been absolutely impossible. You see, most people think quantum mechanics is weird because particles can be in two places at once, or because cats can be both dead and alive. And sure, I helped make those ideas famous. But here's what I've never been comfortable admitting: those aren't the real mystery. The real mystery is so much stranger, so much more personal, and it took me decades to find the courage to face what it actually means. Let me show you what I saw. And I promise you, once you see it the way I finally did, you'll never look at reality the same way again. Now, I need to take you back to 1963. I was at Caltech, and I'd been teaching quantum mechanics for years. I thought I had it figured out, or at least I'd made peace with it. I could calculate anything you wanted. Electron orbits, photon scattering, the whole business. My path integral formulation was working beautifully, but I had this nagging feeling, like I was using a recipe that worked perfectly, but I didn't actually know why. One afternoon, I was preparing a lecture on the double-slit experiment. You've probably heard of it. You shoot particles at a barrier with two slits, and somehow they create an interference pattern, like waves. Now, I'd explained this experiment hundreds of times. It was old hat. Thomas Young did it with light back in 1801. But this time, I was planning to tell my students about something different, the thought experiment where you send electrons through one at a time. And that's when it hit me. I'd been teaching this experiment for years, but I'd never actually seen it done. Nobody had. The technology didn't exist yet. We were all just imagining what would happen if we could send individual electrons through, one by one, and watch where they landed. See? Here's what conventional quantum mechanics predicted: even if you send the electrons one at a time, so there's only ever one electron in flight, you should still get an interference pattern. Eventually. After thousands of electrons have gone through and landed on the detector screen, you'd see those characteristic light and dark bands, the interference pattern of a wave. But here's what kept me up at night. How does one electron know where the other electrons landed? How does the 1,000th electron know to land in a spot that, together with the previous 999, creates a wave pattern? My colleagues had a standard answer. Each electron goes through both slits as a wave, interferes with itself, and then collapses when it hits the screen. And I would nod, and I would teach this, and I would calculate the probabilities perfectly. But I didn't believe it. Not really. Because when I was honest with myself, late at night in my office, I had to admit I had no idea what was actually happening. And then, in the 1970s, something extraordinary happened. The technology caught up with the thought experiment. Physicists in Italy, Pier Giorgio Merli, Gianfranco Misseroli, and Giulio Pozzi in Bologna, they actually did it. They built an electron microscope that could send electrons through a double-slit one at a time. And they photographed what happened. I got wind of their results, and I remember sitting in my office, staring at their photographs, and feeling this sensation I hadn't felt since I was a young man, complete intellectual vertigo. Let me tell you what those photographs showed me. And more importantly, let me tell you what I realized when I saw them. The Bologna experiment worked like this. They had an electron gun that could fire electrons so slowly that only one was in flight at any moment. One electron would leave the gun, travel through the apparatus, pass through the double slit, and it would hit a detector screen and make a single point of light, like a tiny flash. Then, after that electron had landed and was done, completely finished with its journey, they'd send the next one. Now, here's what I want you to imagine with me, because this is what I did. I sat there and I imagined watching this happen in real time. The first electron goes through. It lands somewhere on the screen. Looks random. Second electron. Different spot. Still seems random. Third, fourth, fifth. Just scattered points. No pattern at all. After 100 electrons, you've got 100 dots sprinkled around the screen. And here's what's remarkable. If you look at just these 100 dots, you can't see any pattern. It looks like they're landing randomly, like someone threw paint at a canvas. But then you keep going. 200 electrons, 500, 1,000, and gradually, like watching a photograph develop in a darkroom, something starts to emerge from the randomness. The dots start to cluster. Some areas of the screen get more dots. Other areas stay darker, fewer dots land there. And after several thousand electrons have landed, one by one, separated in time, never overlapping, you see it. Stripes, the interference pattern, the unmistakable signature of a wave. Now, when I first saw these photographs, the actual experimental results, I had the same reaction I'd been having for 30 years. Well, of course, that's what quantum mechanics predicts. I could write down the wave function, calculate the probability distribution, and the math worked out perfectly. But then I did something I hadn't done in a long time. I stopped calculating and just looked at what was happening. Let me tell you what I noticed. Each electron lands as a particle, a single discrete dot. Never smeared out, never fuzzy. You can point to exactly where it hit. That electron landed there. There's no wave on the screen. There are only particles. But the pattern they form together, that's the pattern of a wave. So I asked myself, where was the wave? When was it a wave? The standard answer, the one I'd taught for decades, was that each electron travels as a wave, goes through both slits, interferes with itself, and then collapses into a particle when it hits the screen. But here's what bothered me. If that's true, if each individual electron is really a wave that goes through both slits, why does it always collapse into one dot? Why don't we ever see it splattered across the screen in its waveform? Why does it always, without exception, land as a particle in exactly one spot? And more than that, if each electron goes through both slits and creates its own individual interference pattern, then why doesn't one electron show any interference? Why do you need thousands of them before the wave pattern appears? I started to feel like I was watching a magic trick. And I knew there had to be something I was missing, something in the way I was thinking about it that was keeping me from seeing what was really happening. So I went back to basics. I went back to something I'd been working on since the 1940s, the path integral formulation. You see, in my approach to quantum mechanics, you don't think about a particle taking one path from A to B. Instead, you consider every possible path it could take, straight paths, curved paths, loops, zigzags, completely crazy paths, and you add them all up with different phase angles. The interference between all these paths gives you the probability of where the particle will land. I'd been teaching this for years. But now, looking at these photographs of single electrons building up an interference pattern, I started to wonder, what if I took my own formulation more seriously than I'd been willing to before? Let me tell you about a conversation I had with myself. It sounds crazy, but this is actually how I think. I argue with myself. I take different positions and fight it out until something gives way. So one version of me said, "Look, Dick, it's simple. Each electron is described by a wave function. The wave function goes through both slits. It interferes with itself. When the electron hits the screen, the wave function collapses, and you get a dot. The wave function gives you the probability of where that dot will appear. What's the problem?" And another version of me, the version that had been bothering me for decades, said, "But what is this wave function? Is it real? Is it just mathematics? And what do you mean it collapses? What physically happens during this collapse?" Now, I'd had this argument with myself before, many times. Usually, I just pushed it aside and got back to calculating. But this time, looking at those photographs, I couldn't let it go. So I tried something different. I tried to watch an electron in my mind's eye, really watch it, as it went through the experiment. Imagine an electron leaves the gun. At that moment, it's definitely a particle. It came from a specific atom in the electron gun's cathode. Now it's flying through space toward the barrier with two slits. Here's where the conventional story says it becomes a wave and goes through both slits. But wait, let's actually think about that. What does it mean for one electron to go through two slits? Does it split in half? No, that's not what anyone claims. The electron isn't divided. Does it go through one slit and the other slit at the same time? That sounds like mysticism, not physics. Or does it somehow go through both slits as a wave, whatever that means, and then turn back into a particle when it lands? I sat with this for weeks. And then I remembered something Niels Bohr told me years ago, back when I was a young man at Princeton. We were arguing about quantum mechanics. We argued about it constantly, and he said something that frustrated me at the time. If you're not confused by quantum mechanics, you haven't really understood it. I'd always thought that was an excuse, a way of avoiding a real explanation. But now I wondered if Bohr was pointing at something I'd been too arrogant to see. So I went back to my path integral formulation. But this time I tried to visualize it differently. Instead of thinking about the electron as either a particle or a wave, I tried to think about what the mathematics was actually telling me. In the path integral approach, you don't ask, which slit did the electron go through? Instead, you say, the electron took every possible path from the gun to the screen, and these paths interfere with each other. Now, I'd always thought of this as just a mathematical trick, a clever way to do the calculation. But what if it was more than that? What if the electron actually took all those paths? But wait, how can one electron take multiple paths? That sounds even worse than going through both slits! And that's when I realized I was still thinking about the electron as a little ball, a tiny classical object that has to be in one place at one time following one path. But what if that picture, that intuition I'd been carrying around since childhood, was simply wrong for quantum objects? Let me try to explain what I started to understand. And I warn you, this is where it gets uncomfortable. This is where I had to give up something I'd been holding onto without realizing it. An electron isn't a tiny ball. It's not a little wave either. It's something else, something we don't have a good word for in English. The mathematics calls it a quantum field excitation, or a probability amplitude distribution. But those are just fancy words that hide the fact that we don't really have an intuitive picture for what it is. What we have instead is a description of what it does. And what it does is this: it behaves in a way that's consistent with having taken all possible paths from the source to the detector, with each path contributing a certain amount to the final probability. In other words, the electron doesn't go through the left slit, or go through the right slit, or even go through both slits. Those phrases assume the electron is a classical object with a definite trajectory, but it's not. The electron is in a quantum superposition state, and I know that's a piece of jargon, but what it means is that asking, which slit did it go through, is like asking, what does the color blue smell like? It's a grammatically correct question that doesn't actually mean anything in this context. Now, I know what you're thinking, because I thought it too. That's just word games, Dick. Stop hiding behind the math and tell me what's really happening. And here's what I realized, sitting in my office, staring at those photographs. I couldn't. Not because I was stupid or lazy, but because what's really happening doesn't fit into the categories my brain evolved to understand. My brain evolved to understand rocks and rivers and antelope, objects that are always in one place at one time, following one path through space. My intuitions are perfectly calibrated for that world. But electrons don't live in that world. And here's the kicker, the thing that really bothered me. I'd been teaching this for decades, but I'd been teaching it as if it was just a technical detail, a quirk of small things. I'd say, quantum mechanics is weird, but we can calculate it, so let's move on. But it's not a technical detail. It's a fundamental statement about the nature of reality. And I'd been avoiding it. Let me tell you what happened next, because this is where my understanding completely shifted. I was talking to one of my graduate students, bright kid, always asking uncomfortable questions, and he said, "Professor Feynman, if each electron really takes all possible paths, then why does it always land in just one spot? Why don't we see it spread out across multiple positions when it hits the screen?" and I started to give him the standard answer about wave function collapse, about how measurement forces the electron to choose a position. But halfway through my explanation, I stopped, because I realized I was just reciting words I'd memorized, not explaining something I actually understood. So I said, "You know what? I don't know. Let me think about it." And I went back to my office, and I really thought about it. Not about the mathematics, I could do the mathematics in my sleep, but about what was physically happening when an electron hits a detector screen. Here's what I realized. The detector screen is also made of quantum particles, atoms, electrons in those atoms. They're all governed by the same quantum rules. So when my electron, the one flying through the experiment, interacts with the screen, it's not interacting with a classical measuring device. It's interacting with billions of other quantum particles. And that interaction is a quantum process. The electron's quantum state becomes entangled with the quantum states of the atoms in the screen. And through those atoms, it becomes entangled with more atoms and more until the entanglement spreads out into the entire environment. The air molecules in the room, the photons bouncing around, the molecules in my eyes if I'm watching. This process is called decoherence, and it happens incredibly fast. In a fraction of a nanosecond, the quantum superposition of the electron's position gets entangled with so many other particles that, for all practical purposes, the electron now has a definite position. The universe has recorded where it landed. But here's the thing that blew my mind. The electron didn't choose to be in that position. There wasn't a moment where it suddenly decided, okay, I'll be here instead of there. What happened is that the quantum state of the entire system, electron plus detector plus environment, evolved according to the Schrödinger equation. And from my perspective, observing the outcome, it looks like the electron suddenly acquired a definite position. But really, the universe split into multiple branches, and I'm observing the outcome in this branch. Now, wait, I need to be careful here. I know how this sounds. Multiple universes. Come on, Dick, you've gone off the deep end. And look, I was skeptical too. The many worlds interpretation, proposed by Hugh Everett back in the 1950s, always sounded like science fiction to me. But the more I thought about the double-slit experiment with single electrons, the more I realized that every other interpretation had even bigger problems. The Copenhagen interpretation says the wave function collapses when you measure it. But what counts as a measurement? Where exactly does the collapse happen? When? These questions don't have good answers. Hidden variable theories, like the ones Einstein hoped for, say there's some deeper reality underneath the quantum probabilities. But John Bell proved those don't work unless you allow for faster. Then light influences, which violates relativity. The many worlds interpretation says nothing collapses. The wave function always evolves smoothly according to the Schrödinger equation. When an electron hits the detector screen, the universe branches into multiple worlds, one for each possible landing position. In each branch, observers see the electron in one definite spot, and the number of branches corresponding to each region is proportional to the squared amplitude of the wave function in that region, which is exactly what we call the probability in standard quantum mechanics. So in this picture, every single electron that went through the double slit in the Bologna experiment created thousands of branches, one branch for every possible landing position. And in most of those branches, the electron landed in the bright fringes of the interference pattern. In fewer branches, it landed in the dark fringes. I exist in one of these branches. I see one outcome, but there are copies of me in other branches, seeing different outcomes. Now, I'm not going to tell you this is definitely true. I'm not going to tell you I've solved quantum mechanics and I know exactly how reality works. But I will tell you this, taking this interpretation seriously helped me understand something about the single electron double-slit experiment that I'd never grasped before. Each individual electron doesn't know where to land to create an interference pattern. Instead, the pattern emerges because the wave function, which describes the quantum state before any branching happens, has high amplitude in some regions and low amplitude in others. When the branching occurs, more branches have the electron in high amplitude regions, fewer branches have it in low amplitude regions. Over thousands of runs of the experiment, thousands of branchings, I and my detector screen end up in a branch where the accumulated dots form the interference pattern. Not because the electrons conspired to make that pattern, but because the pattern was encoded in the wave function all along, and the branching process revealed it statistically. Does this make sense? I don't know. Does it correspond to what's really happening? I really don't know. But here's what I learned from this struggle. The mystery isn't that electrons behave strangely. The mystery is that our intuitions about reality, built from everyday experience with large objects, completely break down at the quantum scale. And maybe the most honest thing I can say is, I don't know what an electron really is, but I know how to calculate what it will do. And when I watch it do that, one electron at a time, I'm filled with wonder. Let me tell you about a lecture I gave in 1964, part of what became the Feynman lectures on physics. I was talking to my undergraduate students at Caltech about this very experiment, the double slit with single electrons, and I said something that I'd been thinking about for a long time. This is impossible to explain classically and has in it the heart of quantum mechanics. In reality, it contains the only mystery. I meant that. Everything strange about quantum mechanics, all the weird behavior, all the counterintuitive results can be traced back to this single phenomenon, the interference of probability amplitudes. When you understand why a single electron creates an interference pattern, you understand quantum superposition. You understand why Y particles can be in two places at once before measurement. You understand entanglement. You understand why quantum computers work. You understand why quantum tunneling happens. It's all there in this one elegant, mysterious fact: probability amplitudes. These complex numbers that describe quantum states add together like waves and interfere with each other. And only after they interfere do you square them to get actual probabilities. That's it. That's the whole mystery. And it's enough to make reality fundamentally strange. But here's what I want you to understand. What took me decades to really feel in my bones. This isn't a flaw in our theories. This isn't a sign that we're missing something or that we need to dig deeper. This is how nature works at the most fundamental level we've been able to access. And when I finally accepted that, really accepted it, not just as a formula, but as a fact about reality, something changed in how I saw the world. You see, everything around you, the screen you're looking at, the light carrying this information to your eyes, the atoms in your body, all of it is made of quantum particles obeying these strange rules. The reason everyday objects seem normal and classical is just that they involve so many quantum particles that the weird effects average out. The branches of the wave function decohere so quickly that you never perceive the superposition. But it's there, always. You are a quantum phenomenon. Your consciousness is emerging from quantum processes in your neurons. Every photon that enters your eye and lets you see is a quantum particle, traveling as a superposition of paths until it hits your retina. I remember walking home from my office one evening, after spending hours thinking about these photographs of single electrons. And I looked up at the stars, and I thought every photon from those stars traveled billions of miles through space as a quantum wave. And when it hit my retina just now, the universe branched, and in this branch, I saw that particular star. There are versions of me in other branches who saw slightly different configurations of stars because different photons made it to their eyes. An infinite proliferation of slightly different experiences, all equally real, all branching from the same quantum origin. Now, maybe that's not the right way to think about it. Maybe the many worlds interpretation is wrong, and there's some other explanation. But right or wrong, thinking about it this way helped me understand something important. The measurement problem in quantum mechanics, the question of why we only see one outcome instead of the superposition, isn't a separate mystery from the double double-slit experiment. It's the same mystery. When you watch an electron hit a screen, you're not outside the quantum world looking in, you're part of it. Your observation is a quantum event. You become entangled with the electron state. And that means the question, where did the electron land, is inextricably tied to the question, which version of me observed it? This is what Bohr was trying to tell me all those years ago. The observer and the observed can't be separated in quantum mechanics. Not because of some mystical connection, but because both are quantum systems obeying the same laws. But here's where I part ways with the old Copenhagen interpretation. Bohr seemed to think this meant we couldn't talk about reality independent of observation, that the electron somehow didn't have properties until we measured them. I don't buy that. I think the electron has a quantum state, described by its wave function, whether we're looking or not. It's just that the quantum state is fundamentally different from the properties we're used to in classical physics. The electron doesn't have a position until it interacts with something that forces decoherence. But it does have a wave function, and that wave function is real and has physical consequences. The interference pattern in the double-slit experiment is proof that the wave function is real. Because each electron, traveling one at a time, still knows about both slits. The wave function extends through both slits, and when the electron lands, the position it takes is governed by that wave function. So the wave function isn't just a mathematical tool for calculating probabilities. It's a real physical field that exists in space, or rather, in a more abstract configuration space, and governs the behavior of quantum particles. And that means that when I see one electron make one dot on a screen, I'm seeing the endpoint of a quantum process that involved real interference between different parts of the electron's wave function. Parts that went through the left slit and parts that went through the right slit. The wave function is nature's way of keeping track of all possibilities simultaneously, letting them interfere, and then, through decoherence, creating the appearance of a definite outcome. Now here's what changed everything for me. I was staring at one particular photograph from the Bologna experiment. It showed about 500 electrons, 500 little dots scattered across the screen. You could just barely start to see the hint of an interference pattern. Some regions had slightly more dots, some slightly fewer. And I asked myself, what is this photograph actually showing me? And then it hit me. Really hit me, in a way it never had before. Each of those 500 dots represents a measurement, a point where the quantum wave function of an electron became entangled with the macroscopic world. Each dot is a place where reality branched. But here's the revelation. The interference pattern isn't created by those 500 electrons. It was always there, encoded in the wave function from the very beginning. Before any electron flew through the apparatus, the wave function of electron shot at a double slit already had high amplitude in certain regions and low amplitude in others. The electrons aren't building the pattern, they're revealing it, like invisible ink becoming visible. The pattern exists in the quantum realm. In the wave function, and the electrons, by landing as particles, are making it visible to us in the classical realm. That's why each individual electron seems random, because it is random from our perspective in this branch. But across all the branches where the experiment is run, the distribution of landing positions follows the interference pattern. Always. And here's what stunned me. This means the pattern isn't a property of the electrons. It's a property of the setup. The moment you create a situation with two slits separated by a certain distance, with a coherent source of electrons at a certain wavelength, the wave function automatically develops this interference structure. The electrons are just sampling from that pre-existing probability distribution. So when someone asks me, how does one electron know where the other electrons landed? The answer is, it doesn't. It doesn't need to. Each electron is simply following the quantum rules, interacting with the slits in the way that quantum fields interact with barriers, and the wave function guides where it's likely to land. But more than that, and this is what I really want you to grasp, the electron doesn't travel. through the slits the way a ball travels through a hoop. The electron's wave function interacts with the slits in a way that creates a new wave function on the other side. And that new wave function has interference in it, regions where the contributions from both slits add up constructively, and regions where they add up destructively. This is what my path integral formulation was trying to tell me all along. The electron takes all paths, including paths through both slits, and these paths interfere with each other in the wave function, which then determines the probability of where the electron lands. So the answer to which slit did the electron go through is neither. Both. All of them. The question doesn't have a classical answer because it presupposes a classical reality, one where particles have definite trajectories. But there's something even deeper here. Something that took me years to appreciate. When I was young, I thought physics was about discovering what the world is made of. First we found atoms, then electrons and protons, then quarks and gluons. I thought we were peeling back layers, getting closer to the fundamental stuff of reality. But the double-slit experiment with single electrons taught me something different. It taught me that reality at the quantum level isn't made of stuff in the way I thought. It's made of fields and interactions and possibilities that crystallize into definite outcomes only when they become entangled with larger systems. An electron isn't a tiny ball. It isn't a wave. It's an excitation in the electron quantum field, a ripple in a more fundamental fabric of reality. And that ripple has properties that don't fit neatly into particle or wave categories. It has particle-like properties when it interacts strongly with localized systems. It has wave-like properties when it's isolated and free to spread out. The reason the double-slit experiment seems paradoxical is that we're trying to fit quantum behavior into classical categories. We're asking particle or wave, when the answer is neither something else. And once I accepted that, once I stopped trying to force quantum mechanics to make sense in terms of my classical intuitions, the mystery didn't disappear, but it changed. It became less frustrating and more beautiful, because what I realized is this: the universe is fundamentally stranger and more subtle than I ever imagined as a young physicist. And that strangeness isn't a bug, it's the most elegant feature. It's what allows reality to be both concrete and fluid, both determined and probabilistic, both singular and multiple. The single-electron double-slit experiment isn't showing me a flaw in reality. It's showing me how reality actually works. And it works through quantum interference, this magnificent, mathematical dance of probability amplitudes that underlies everything. You know, I've spent most of my life calculating things. That's what theoretical physicists do. We write down equations, we solve them, we predict experimental outcomes. And I've been good at it. I'm proud of that. But there are moments, rare moments, when the calculations fade away and I'm left just looking at nature, trying to see it clearly. The single-electron double-slit experiment gave me one of those moments. Every time I think about it one electron at a time, each one making a single dot, thousands of them slowly revealing the interference pattern, I feel this sense of, I don't know how to describe it, vertigo. Ow. Humility. Because what I'm seeing is the universe being more clever than I am, more subtle, more profound. I'm seeing that my intuitions, built from a lifetime of experience with everyday objects, are completely inadequate for understanding the microscopic world. And yet, somehow, I can still understand it. Not intuitively, but mathematically. Through equations that capture what's happening, even though I can't visualize it. That's what physics is really. It's not about having the right intuition. It's about building mathematical models that work, that make predictions, that reveal patterns, and then living with the strangeness of what those models tell us. For decades, I taught quantum mechanics to students. And I always warned them, nobody understands quantum mechanics. I meant it. I still mean it. But I understand it better now than I did then. Not because I've solved the mysteries, but because I've accepted them more fully. I've accepted that an electron is not a tiny ball following a trajectory. I've accepted that asking, which slit, is a meaningless question. I've accepted that observation is a physical process that entangles me with the system I'm observing. I've accepted that reality at the quantum level is described by wave functions in abstract spaces, and those wave functions don't correspond to anything I can easily visualize. And you know what? Accepting all that doesn't make physics less magical. It makes it more magical, because look at what we've accomplished with this strange, counterintuitive theory. We've built transistors and lasers. We've explained why atoms exist, why chemistry works, why the sun shines. We've created quantum computers that can solve certain problems exponentially faster than classical computers. We've developed quantum cryptography that's provably secure. All of that comes from taking quantum mechanics seriously. From accepting that particles interfere with themselves, that measurement changes reality, that the universe is fundamentally probabilistic at the smallest scales. The single-electron double-slit experiment is a window into that strange quantum world. And what makes it so powerful, what makes it, as I said to my students, the only mystery, is that it's so simple. You don't need a giant accelerator or a billion-dollar detector. You just need one electron, two slits, and a screen, and the patience to send electrons through one at a time and watch the pattern build. In those building dots, random individually, patterned collectively, you see the entire quantum mystery laid bare. You see that reality is not what you thought it was, that the solid, definite world you experience is built on a foundation of probability and interference and superposition. And for me, that's not a depressing thought. It's a liberating one. It means the universe is far richer than our everyday experience suggests. It means there are depths to reality that we're only beginning to explore. It means that the questions we can ask about the nature of time, the origin of the universe, the relationship between consciousness and quantum mechanics are still wide open. I don't know the final answers. I don't think anyone does. Maybe there aren't final answers, maybe just deeper and deeper questions. But that's okay. That's what makes this adventure worth taking. So here's what I hope you take away from this. The next time you hear someone say, "Quantum mechanics is weird," I want you to think about that single electron traveling through the double slit, landing as one dot among thousands. I want you to remember that the weirdness isn't a mistake or a confusion. It's a discovery, a revelation about how nature actually works. And I want you to feel what I feel when I think about it: wonder. Pure, childlike wonder at the fact that reality is so much stranger and more beautiful than we ever expected. That's the real mystery. Not that we can't understand quantum mechanics, but that we can understand it at all, even though it violates every intuition we have. We can't visualize it, but we can describe it. We can predict it. We can use it. And sometimes late at night, when I'm alone with my thoughts, I look at pictures of that interference pattern, built one electron at a time, and I think, the universe let me see this. It let me glimpse how it works at the deepest level. What a privilege. That's what physics is for me. Not certainty, not comfort, but the privilege of seeing nature as it really is, even when it's stranger than I can imagine. And that's enough. That's more than enough.